For centuries, they were theoretical, then invisible. Everyone thought a black hole could never be photographed. They were wrong. On April 10, 2019, humanity saw a black hole for the very first time. Not an artist's rendering, not a simulation, but an actual image, a fuzzy orange donut against the cosmic void. It was a scientific triumph decades in the making, the culmination of human ingenuity pushing against the very limits of physics. This wasn't just a pretty picture. It was a profound validation of Einstein's general theory of relativity, a theory that predicted these cosmic behemoths with chilling accuracy over a century ago. Imagine a theory so robust, so prescient, it could foretell something so utterly alien, so completely hidden. For much of the 20th century, black holes were the stuff of science fiction, mathematical curiosities, or at best, indirect observations. We knew they were there, by their immense gravitational pull on nearby stars, by the X-rays emitted from superheated gas spiraling into their maw. But seeing one, that seemed impossible. The challenge was immense. Black holes are, by their very nature, invisible. Not even light can escape their gravitational grasp once it crosses the event horizon. It's the ultimate cosmic trap. So how do you photograph something that doesn't emit light? The answer lies not in seeing the black hole itself, but in seeing its shadow. Imagine a lighthouse in the middle of a dense fog. You can't see the lighthouse, but you can see the light it casts. A black hole works similarly, but in reverse. It casts a shadow against the glowing hot gas and dust surrounding it. This glowing ring of superheated plasma, accelerating to near the speed of light, emits powerful radio waves. This is what the Event Horizon Telescope aimed to capture. But even this glowing ring is incredibly small, especially from Earth. The target black hole, Messier 87 M87*, at the center of the Virgo, a galaxy, is 55 million light-years away. To put that in perspective, capturing its shadow would be like trying to read the date on a quarter placed on the surface of the moon. A quarter from 55 million light-years. To achieve such an unprecedented resolution, astronomers needed a telescope the size of the Earth itself. Of course, building such a monolithic instrument is impossible, so they did the next best thing. They built a virtual one. This is where the Event Horizon Telescope, or EIT, comes in. It's not a single telescope, but a global network of 8 synchronized radio observatories spanning 4 continents. From the frigid South Pole to the volcanic peaks of Hawaii and the deserts of Chile, these dishes worked as one. The technique is called Very Long Baseline Interferometry, or VLBI. By precisely timing the arrival of radio waves at each dish and combining their data, scientists can synthesize an image with the resolution equivalent of a single telescope dish as wide as the distance between the farthest observatories. But synchronizing these dishes required atomic clocks, accurate to within a fraction of a nanosecond, and petabytes of data recorded on hard drives. Imagine coordinating a global orchestra where each musician is playing from a different continent, all perfectly in time. The observations took place over 4 intense days in April 2017. Weather conditions had to be perfect at all 8 sites simultaneously, a rare occurrence. Any cloud cover or atmospheric moisture could disrupt the radio signals. After the data was collected, it wasn't simply beamed to a central location. The sheer volume was too massive. Instead, hard drives packed with petabytes of raw information had to be physically flown to 2 central processing centers, MIT Haystack Observatory in Massachusetts and the Max Planck Institute for Radio Astronomy in Germany. At these supercomputing facilities, specialized algorithms spent months piecing together the fragments of data. It was like trying to reconstruct a complex jigsaw puzzle with pieces collected from around the world, each piece arriving at a different time, and some even slightly distorted. A team of over 200 scientists from 60 institutions across 20 countries worked tirelessly on this monumental task. They were not just processing data, they were inventing new ways to process data, pushing the boundaries of computational astrophysics. The result, finally unveiled on April 10, 2019, was an image that instantly became iconic. A shimmering, asymmetric ring of light, with a darker void at its center, the shadow of M87 asterisk. It was a direct visual confirmation of what Einstein had predicted. The asymmetry of the ring wasn't an error, it was another triumph. The side that appears brighter is gas moving towards us, experiencing a Doppler boost, while the dimmer side is moving away. This provided crucial evidence that the accretion disk was indeed rotating, exactly as theories suggested. Beyond M87 asterisk, the EHT also targeted Sagittarius A asterisk, the supermassive black hole at the center of our own Milky Way galaxy. Though closer, SGR A asterisk is smaller and far more active, like a restless toddler constantly changing its appearance. Imaging SGR A asterisk proved even more challenging due to its variability. But after several more years of meticulous data collection and processing, in May 2022, the EHT delivered its second historic image, the shadow of our galaxy's own monster. These images aren't just pretty pictures, they are invaluable tools. They allow scientists to test general relativity in extreme environments, to study how black holes grow and how they influence the evolution of galaxies. It opens a new window into the most mysterious objects in the universe. The Event Horizon Telescope project continues to expand, with new observatories joining the network. This will lead to even sharper images, perhaps even allowing us to capture real-time movies of the dynamic environment around black holes. Imagine that. From theoretical constructs to tangible photographs, the journey of black holes in our understanding mirrors humanity's insatiable drive to explore, to question, and to push the boundaries of what is possible. It reminds us that even the most formidable cosmic mysteries can, with enough ingenuity, be brought into the light. Next, let's explore the chilling possibility of rogue black holes wandering through interstellar space.